Unit 6, pages 112 to 117, the Bohr model of the atom. Niels Bohr proposed the first modern model of the hydrogen atom, where he basically said electrons are moving around the nucleus as though planets orbit around the sun in very specific centrifugal orbits. And there's an inward electromagnetic force pulling towards the proton and an outward centrifugal force that the electron has as it is in motion that keeps it from moving towards the nucleus. The centrifugal force felt by the electron as it moves on a circular orbit is the same outward force you would feel driving in a car around in a circle. This model is now known not to be completely correct. Electrostatic positive and negative attraction balances the centrifugal force. This theory broke with classical physics by suggesting only certain orbits are possible because the electron orbit must contain an integer number of electron wavelengths. Remember that particles have wave properties, so a moving electron is a wave. And here's a diagram of the particle wave of the electron in its orbit. The resulting equation for the allowed energies of electrons has only certain energies. The energies are quantized. So basically each energy level or distance from the nucleus has a specific amount of energy, and there is no in-between. You can't be between levels. So energy is equal to the negative Rydberg constant divided by the energy level squared. In this equation, n is an integer called the quantum number. Rydberg's constant is 2.18 times 10 to the negative 18 joules. The Rydberg constant, RH, is specific for hydrogen. Bohr's theory exactly predicts the observed light coming out of an excited hydrogen atom, and it's the beginning of a new physics to describe the atomic properties. Bohr's equation for the lines in a hydrogen spectrum. So consider here the electron is on energy level 2. In order to move down to energy level 1, it has to emit energy. And then to move from energy level 1 back up to energy level 2, it has to absorb energy. And so here's the same idea, but in more of a graph, where you have energy level 1, and you have to absorb energy or have a positive intake in energy to move to energy level 2. N equals 1, N equal to 2. And then if you want to move back down from n equal 2 to n equal 1, then energy out is going to be a negative, or emission. Bohr's theory showed that each allowed orbit had a certain specific energy. When an excited hydrogen atom changes from a higher energy orbit to a lower orbit, energy is emitted in the form of light. The equation for the energy of the light is going to be the difference between the two energies, which is equal to the negative Rydberg over the upper energy level minus the negative Rydberg over the lower energy level. In this equation, Nu is the quantum number of the upper level, higher energy, and Nl is the quantum number for the lower level. Using the equations for light, here, two other equations for the light emitted from a hydrogen atom can be obtained. So combining all of these equations, we basically get down to these two Rydberg equations, where you can determine the frequency of the light emitted when an electron moves from an upper level to a lower level, or you can get the wavelength when you move from an upper to a lower level with this equation right here. Exercise 6.36. What is the wavelength of light emitted, so find the wavelength, emitted from a hydrogen atom when a transition is made from n equal 3 to n equal 1 level? And so we're going to want to use one of those equations above. This Rydberg equation allows you to solve for the wavelength. So let's plug in our values for the Rydberg constant, Planck's constant, the speed of light, and then our upper level, which is 3, and our lower level, which is 1. The challenge with this problem lies in putting it in your calculator. So first, I'll start with these parentheses over here, open parenthesis 1 divided by 3 squared, and then minus basically 1 over 1 squared, which is just 1. Close the parentheses. I'll go ahead and hit equals and get that value. And now I'm going to multiply it times this numerator, which is negative 2.18 times 10 to the negative 18. And then I'll go ahead and divide by, open parentheses, 6.63 times 10 to the negative 34 times 3 times 10 to the 8, close parenthesis, and I'll get this value. However, this is not equal to the wavelength, it's equal to 1 over the wavelength. So in order to get this answer, I'm going to have to take the inverse of this value, which means I'll hit to the negative 1, and then hit equals, and that'll get me a value of 1.03 times 10 to the negative 7, and that's going to be meters. Typically, light is expressed in a unit of nanometers, so 1 meter is equal to 1 times 10 to the 9 nanometers, which is going to give us 103 nanometers is the wavelength of the light emitted whenever we move from energy level 3 down to energy level 1. Exercise 6.37. What is the frequency of light absorbed by a hydrogen atom when a transition is made from n equal 1 to n equal 3 level? So here's the equation to solve for frequency. It's going to be the negative Rydberg constant over Planck's constant times 1 over 3 squared minus 1 over 1 squared. So let's set that up. And so now we'll type it into our calculator. I'll take care of this first. So open parenthesis, 1 divided by 3 squared minus 1. Close parenthesis. Go ahead and get that answer. And then I'll multiply times the numerator times negative 2.18 times 10 to the negative 18 equals, and I'm going to divide by, and just for safe measure, I'm going to put it in parentheses, 6.63 times 10 to the negative 34 close parenthesis, because otherwise it's only going to divide by the 6.63 and then it'll multiply your entire answer by 10 to the negative 34, which we don't want. We want to divide by this whole Planck's constant value. And we're going to get 2.92 times 10 to the 15 as our frequency. Remember, that's in a unit of hertz, although you could put it as 1 per second, or you can put it as seconds to the negative 1. All three of those represent the same thing. So this diagram shows the energies of the hydrogen atom. The highest energy level when the proton and electron are separated by an infinite distance has an energy of 0 and an n equal to infinity. So this would be like when ionization energy occurs, where an electron has enough energy has hit it that it's knocked it out of the atom, and so it moves infinite distance away from the nucleus, which means it has an energy of 0. The highest energy level when as the electron gets closer to the nucleus, the energy levels become more negative. So you'll notice here that as you become closer to the nucleus, the energies become more and more negative, and when you are at the nucleus, then it is the negative Rydberg constant. The level n equal 1 is the lowest energy, smallest orbit called the ground state. Higher energy levels, like n greater than 1, are called excited states. And this is for a hydrogen atom because there's only one electron in hydrogen. So this is the ground state of the electron in a hydrogen atom, and then anything beyond that is going to be an excited state unless you get to this point, in which case we have ionization, we have hit with ionization energy and ejected the electron from the atom altogether. So here are the problems with the Bohr's theory. Many additional properties of atoms could not be explained by Bohr's theory. Solving these problems lead to the development of the modern quantum theory. Number 1, 4 quantum numbers are needed to describe each electron where Bohr's theory only had 1. It became clear that electrons did not move on precise fixed orbits. The shapes of the regions in space occupied by electrons could not be explained by Bohr's theory, and the arrangement of electrons and the energy levels could not be explained by Bohr's theory.